All right, shall we get started? I guess I should introduce myself before I forget, because I almost always forget to introduce myself. I am Nadab. I used to develop full-time and do DLC stuff, and now I'm a PhD student, so that's what I am. We're going to be mostly working kind of with people around you, chatting. If you have any paper and pencil, that could always be useful. They'll be more useful than your computers. We're not going to be coding during this workshop, so if any of your friends have paper and pencil, perhaps you can share. And speaking of which, you should introduce yourself to the people around you. I'll give you a couple minutes, because we don't want to just jump right into the math and ignore each other's humanity. So I'll just give you a couple minutes and introduce yourself to the people around you, say hello, and I'll pull you back in a couple minutes. Okay, so the goal is to learn about zero-knowledge proofs, and the definition is a little lengthy, so I'm just going to start out with some demos. Can I have a volunteer? Anyone want to be a volunteer? Want to learn something but not learn much? Yeah, come on up here. All right, so I'm going to shout because my hands are full. I've got two identical looking coins right here. Can everyone see them? Do they look pretty similar? Here, you can take a look. Too close.
They look kind of identical.
Great.
Yeah, well, they look identical.
I won't look at any like stuffs or anything, I promise. I'm not cheating that way. I'm cheating a different way. Okay, great. So I'm going to convince you that I know the difference between these two coins, yes? So here's what's going to happen. I'm going to make sure I am totally set up. Okay, great. And then I'm going to hand these to you. This is your left hand, and this is your right hand. Okay, put them behind your back. And I won't look, and either switch them or don't. But keep track. If you don't know, it's not so useful. And then tell me when you're done.
I'm done.
Okay. Hopefully at least some people saw, so give them here. And then I'll take a look. And, just think for a bit. And you didn't change them.
You're right.
Awesome. Okay, how convinced are you that I know the difference between these?
50%.
Okay. That's pretty much okay. I'd like you to be a little more convinced. Let's just, let's repeat that. Let's do it again. Am I good?
Yeah.
Okay. Here. All right. You did change them.
Yeah.
Awesome. Okay, I'm on a roll. How convinced?
Let's see.
Yeah, let's think.
5%, I guess.
How convinced should he be? What do people think? 75? 25? Wait, he should be less convinced. I got it right. Come on. Yeah, okay, right. 75%, because if I'm just guessing randomly, and it's a coin flip, no pun intended, then I should only have a 50% chance each time, and so the fact that I got it twice, there's only a 25% chance that I'm getting lucky. So, shall we do it one more time just for good measure? You know, 75. What's next? 87 and a half, yeah? Okay. They would be independent if I was lying, and they are the same coin. Yes, good question. Am I good?
Yep.
Okay. Let's see if I remember what I'm supposed to in order to be able to do this. You didn't change them.
Yeah.
Yes.
Actually, I changed them twice. I just wanted to check if you had.
Yeah, good. Awesome, thank you so much. I'll do another demo now. You can have a seat. Okay, so that hopefully convinced you that I know the difference between these two coins, but hopefully you haven't learned anything about the difference between these two coins. So we're on our way. Can I have another volunteer? Yeah, come on up. All right. So let's go. I'm going to have you pick a card. Don't look at it, though. Just pick a card at random. Great. Picked a card. There's a hole in all of them. Yeah. All right. And now I'm going to tell you something about your card, but I'm not going to tell you anything else about your card. So let's see. There we go. Here, I claim, are all of the black cards in the deck. And I promise I'm not good at sleight of hand. Cool. So I have all the black cards here, and your card's here. So what do you know about this card? Oh, I should have made you check that I have all of the cards. I promise I have all the cards in the deck to begin with. So it's red. Exactly. Do you know anything else about it? Ace of clubs. It's right there. Good. Yes, good to check me.
I don't know anything else about it.
Awesome, perfect. That's all I needed. Thank you. Okay, so another demonstration. I've shown something about.
You split the deck into red cards.
I did,
cards,
yes.
and then
Just to make it
whichever
easier
one
for
it
myself.
is, you split it in half and then spread out the cards.
Yes, I cheated. But nonetheless, you still don't know what your card is. All right, and this last one's a bit more involved, but it's good to have some more interesting examples before we start talking about what these are and how we might build them. So, I kind of want to move this. No one stopped me. Okay. Who here is not familiar with Sudoku? Do I need to explain how Sudoku works? Okay, great. So if I actually did like a 9x9 Sudoku here, that would take so long. So we're going to do a little 4x4 demonstration. Yeah, same thing. It's like boxes of 2x2. I've got 4 of them, rows and columns, all that stuff. Okay, so there it is. Okay, so I've got this grid, and these are emphasized. Cool. And to make sure I get it right, I'm going to start with a 1 here, a 3 here, and a 3 here. So this is a puzzle. It's not a hard one. Okay, I bet you could all do it. But what I'm going to do works for like general, larger puzzles. So bear with me. So okay, I want to convince you all that I know a solution to this Sudoku puzzle, but I don't want to tell you anything about it. So here's what I'm going to do. I'm going to start by having, do I do this? Yes, I do this. I'm going to pick one of these at random. These are permutations of the numbers 1 through 4. So if you look at one of these, it says like 1 goes to 1, 2 goes to 3, 3 goes to 2, 4 goes to 4. So this one just swaps 2 and 3. And I totally have all of the permutations here between 1 and 4. That's definitely as much prep as I did. And yeah, anyway, I'm just going to pick one of these at random. Actually, I'm going to start with a different one at random. Okay. Great. And then I'm going to lay out some cards. Sorry if it's a bit rusty. I haven't done this trick in a while. Okay, so these are just numbers I'm putting down. I messed up. Not so bad. Okay, well hopefully I got it right. Okay, so now a random member of the audience can just blurt out. You have 3 options. You're allowed to check one thing. You can either check one of these rows, or sorry, I guess you can check all of these rows, all of these columns, all of these 2x2 boxes. There's a 4th thing, or you can check that here, here, and here are what they're supposed to be. Yeah, so you can either check the rows are correct, the columns are correct, the 2x2 boxes are correct, or my initial setup is correct. So what do y'all want to check? Anyone opinionated? Rows. Okay, cool. So I'm going to take my rows and put them together here. I'm just going to shuffle real quick. I'm very good at precise random shuffling, so these are coming out completely in a random order. All right. Cool. Could I have, you're nearby, what are those numbers? Sure.
1, 4, 3.
Great. With these?
3, 2, 4, 1.
Awesome. What about these?
3, 4, 1, 2.
And these?
3, 1, 2, 4.
Awesome. So are y'all happy or unhappy so far with me? Have I cheated so far that you've caught me in?
No.
No, right? There's the numbers 1 through 4 in each of the rows is what I put down. Now, fun question. I'll give you a moment to talk with your neighbors about this. How convinced should you be so far that, I guess I'll be a bit more precise. If I had cheated in my initial setup, what are the chances that you would have caught me just now? Talk with those around you. I'll give you a minute or two.
We only care.
You would catch me in cheating if there were multiple of the same cards, rows with columns and A by 2 things, or if you asked to see the 3 initial things and they weren't with you.
One no. 3, 2, 1.
All right, what are we thinking? Explore it out.
124.
Okay. How'd you get that? Just out of curiosity.
4 factorial and then 1
Oh, sorry, to be clear, if you check my initial setup, you also get to see the permutation I used.
Wait.
Wait, what?
So yeah, I could do it all again, but yeah, I put down my whole grid, and I have this card that says how I permuted things. And you can either flip over these 3 spots and my permutation card, and make sure that the thing that got sent to, the thing that 1 got sent to is in the top left, and the thing that 3 got sent to is there and there. Or you can check the rows, or you can check the columns, or you can check the 2x2 grids. So yeah, if I didn't know a solution to this, or if there wasn't a solution to this, for example, then one of those 4 things would have to be out of place, right? Either there would be a row that cheated, or there would be a column that cheated, or a 2x2 grid, or I didn't actually use the initial puzzle, right? One of those 4 things has to be violated, otherwise what I have on the table is a solution. And so, if I don't have a solution on the table, then you have at least a 1 in 4 chance of catching me, because one of those 4 things has to be wrong, right? And you're just picking between those 4 options randomly. So if I did it twice, and I got it right twice, how convinced should you be? So chances you catch me, so say I'm alive, then my probability that I fail is equal to 1/4 if we do it once. And what's the probability that I succeed then, right? It's 3/4. And if I succeed twice, I guess you can think of it in 2 ways. So, if I didn't fail the first time and I didn't fail the second time, each chance I only had a 3/4 chance of succeeding as a liar, right? If I don't actually have a solution, if there's no solution. And so the probability that I succeed twice is going to be 3/4 times 3/4, right? Because I got lucky both times. So that'll be what, 9/16, which is, anyone have a calculator or anything? Just so we can get it as a percentage to compare it to make sure that it's getting small. 0.56. Great, so we started out, I had a 75% chance of success if we did it just once, but now I'm already down to about a half. And so doing it twice is about the same as doing my coin thing once, right? Like, if I repeat it not even that many times, you're very quickly going to become very convinced, because as I take 3/4 to higher and higher powers, it very quickly approaches 0.
So in this case, you're trying to prove that you have knowledge about the solution to the puzzle, but every time we ask you to provide either rows or columns, you're actually giving us more information, which makes your secret weaker.
Yeah, let's think about that. So the key here is that say that you're looking at the rows. Since I shuffle the rows, what you see is always a random permutation of the numbers 1 through 4, assuming that I succeed each time. And so I argue, and we'll go into more detail as we get further into the workshop, but I argue that actually you haven't learned anything useful about my solution, because you're just looking at the random numbers 1 through 4 each time you check things. Or, if you check my setup, you're looking at a random permutation and the result of applying that permutation, so 1 and 3 in this case. Yeah, but okay, let's get into what is a zero-knowledge proof. And we'll, of course, revisit maybe this example in a bit. I have an eraser somewhere. Okay, so I'm going to define what a zero-knowledge proof is, and then I'm going to make you come up with one. With your friends, not alone. Alright, so I'm going to start with this definition. A zero-knowledge proof, and I'm just going to write ZKP, because easy, is a conversation between a prover, that was me, and a verifier, that was you. That is convincing and zero knowledge. Of course, I have to expound on what I mean. So by convincing, I mean two things. One, if I'm a liar, if the statement I'm trying to prove is false, then I should fail eventually. So I'll say dishonest prover might fail. And hopefully I've demonstrated that if there's any chance that I fail, if I have any probability of success less than 1, then if we just repeat enough times, eventually that number can be as small as we want it to be. So if I have a 9/10 chance of succeeding as a dishonest prover, and we do it like 100 times, that's still going to be just a tiny number, because 90 over 100 to a high power, y'all can plug it into a computer. I should have brought a calculator. But yeah, so if we have a conversation where the dishonest prover might fail, we can just repeat it, and the dishonest prover will fail with whatever probability we want. And of course, an honest prover always succeeds. This one's kind of obvious, but it just means you constructed it correctly. Great. And then zero knowledge, which is the big topic here, is just saying, and we'll become more precise as the hour progresses, but zero knowledge means that the verifier learns nothing useful other than the statement being proven. All right, I filled the board with the definition. Before we move on, any questions? So I think all three of these example things I showed you are examples of zero knowledge proofs. They were a conversation between me and a verifier, where if I had been dishonest, I had a chance of failure. I think for the coins, I had a 50% chance of failure. For the sudoku, I had a 25% chance of failure. And for the cards, I had a 100% chance of failure if I was being dishonest. And if I was honest, I always had a way to convince you, and I claim that you didn't learn anything other than the statement I was trying to prove. There's not anything useful. We'll have to get into what that means. But any questions before I give you a challenge? Yes?
In practice, we do have protocol which are not where a prover, a dishonest prover might succeed the validation with a very, very low probability, and it's just an assumption of some of the system.
Yes, I'm lying to you, as always. I've been caught. Oh no. Okay, so if I understand what Antoine is telling me, it's that even this is not quite strong enough, because if there's like some chance that I might fail, but it's as small as the chance of, say, being able to guess what the private key is of a given public key, or something like this, then it is essentially the same as not being able to have a chance. Like that chance is too small. So, very well, I'll add a word. I've been caught. Dishonest prover might fail with non-negligible probability. All right, have I satisfied you? Lovely. Good. No, call me out. I'm definitely going to skim over some details that I think won't have a huge effect, but if you notice them, feel free to call them out. Yes?
So it's not really a mathematical proof because it's not absolute.
Definitely. This is what's known as a probabilistic proof. Yep, and in computer science we call those proofs. Yeah, so zero-knowledge proof is an interactive proof. That's what this convincing means, such that it's a zero-knowledge interactive proof. And interactive proofs are, by their nature, only probabilistic. Though, of course, we can have a talk later if you want to get philosophical about whether or not actual mathematical proofs are anything different. All right, topic for another time. Okay, any other questions about the definition now? Are we feeling like we're ready to come up with one of these for ourselves? Okay. Let's do it. So, I keep losing my stuff. Oh, there's this. You all remember these things, right? It all makes sense, so you all have collectively, one of you remembers. Yeah, that's what I need. Yeah. Good point. Okay, so just for the sake of uniformity, and so that you don't get scared when you see these in the wild, usually we're going to draw these as we've got a prover, we've got a verifier, and the conversation will be labeled this way. So for example, if I wanted to take the example of the coins, then basically what happened is that the verifier sent me, so they generated a permutation. So don't be too scared. I could just use a different letter, I guess. I'm so used to pi, because for some reason permutations in this field are oftentimes like plus pi, because it's a Greek P. But fine. What's someone's favorite English letter for a permutation? P? I hate it. Thank you. P could be probability, could be prime, or whatever. Okay. And then we send P of coin 1 and P of coin 2. And then the prover has to respond with like a swap or no swap. And then the verifier checks that this is the same, or I guess I should call this like P hats or something. They make a guess at what P was. And then the question is P the same as P hat? And that's the output for success or not. So this is how I'm going to write these things down. And now I have a challenge for you. So this is an example of how to show that two things that look the same are actually different. So,
What is it in that top line? The arrow on the left, the top arrow on the left.
this?
Yeah.
That's just the permutation applied to coin 1 and the permutation applied to coin 2. So they either gave you, P is either a swap or not a swap. And then they either give you the swap to C1 and C2 or just C1 and C2. Okay, so who knows what people call these things? Yeah, they're called graphs. Doesn't that suck? That we reuse words to mean multiple things and not horrible. But anyway, when I say graph, I don't mean the thing I was drawing yesterday in my workshop with lines and these things. That's a different kind of graph. We're talking about these kinds of graphs today.
These are
Fine. Okay, any kind of graph here. So, a graph, if you want to put it in a computer, we've got Lightning Network developers here in the audience. What are some ways to store a graph in a computer? Nodes and edges. Any other ways?
Matrix.
Yeah, a matrix. It's cool. So there are lots of ways to store these in computers. Anytime you do this, you kind of implicitly have a labeling that you put on. So I'm going to do the matrix thing. say I have like A, B, C, and then I didn't draw the rest of this graph because I wasn't crazy and didn't want to draw a giant matrix. Great. Then how I would put this into a matrix is I would take a square matrix with the labels on the side of the top, and then I would put a 1 if they're connected, so A and B are connected, and A is not connected to A or C, B is also connected to C, and A and C are not connected, and C and C. So okay, here is a matrix, and it's just a 1 if A and B are connected, and it would have been 0 otherwise. Yeah? Okay. This won't be super important for what we're about to do, but it's like good to have in mind that really we're talking about putting things on computers and sending messages back and forth on computers, and that these graphs are just going to be some matrices in a computer. And in particular, if I wanted to change the labeling, I could take a permutation matrix, multiply it on both sides, and it would do that for me. It's like very quick, instantaneous to apply a random permutation, or any permutation, to this matrix to get a relabel. So say that I had drawn a really big graph, say the graph of the Lightning Network, and then I drew a really big other graph that had the same number of vertices and edges, but it was different. Here, somewhere, I don't know. I had a graph G1 and a graph G2, and they were not the same, meaning that there is no way to permute one of them to get the other. Can you prove it in zero knowledge? So my question is, everyone knows what G1 and G2 are. We have a matrix for G1, a matrix for G2, and you, the prover, know that they are different. And the verifier doesn't know that, and they want to be convinced that you actually have two different graphs, just like I convinced you that I had two different coins, that they weren't identical ones, that they were distinguishable. Now I'll just stipulate you as the prover get, let's say, unbounded, just to make things easier, computation time. So you can take all the time in the world you want to do anything you have to do. The verifier is running on a potato-powered toaster, and they can only do fast things. So I'm going to say polytime for now. If you don't know what that means, just think, they can store this, and they can run through it and check simple things. They can do a matrix multiplication. I'm not saying they can't do anything, but they can't, like, brute force stuff. They can't do anything crazy. Okay, so with the people around you, take a minute or 2 or 20, we'll see how long it takes, to see if you can come up with zero-knowledge proof, a conversation between a prover and a verifier, in which the verifier becomes convinced that G1 and G2, these matrices, are actually representing different graphs, and where they don't learn anything else.
Can you repeat that, please?
So we have these two graphs, everyone can see them. They're both computers, they have these in the computers, and the prover wants to prove to the verifier that these are not the same graph. And your challenge is to come up with a conversation to convince a verifier. Good luck. Also, a couple of people walked in. If there's anyone new around you, just introduce yourselves.
Yes. So it's a number of how many votes. Yes. We do have a yes.
Oh, wait.
Well, both prover and verifier have Yes, I forgot to say something. I forgot to mention, so sorry, the problem of determining whether two matrices representing graphs are actually the same graph is a hard computational problem. So if you have a graph and you have a random permutation of that graph, right? Remember, if there's like 100 vertices, there are 100 factorial different ways to write it down in a matrix. And so it is computationally not easy to see that G1 and G2 are the same, so the verifier cannot tell that they're different. Yes? Good questions. Back to you.
You're saying it's 156, 1,029, and actually hard to tell. The verifier is going to figure that out.
Well, sorry, this up here is about I love that one. Yeah. So and that would be a good interaction proof, but it is not zero knowledge because that's what the verifier learns something about why. And so the zero knowledge part, then it doesn't, what you're saying is pretty offensive, but it isn't zero knowledge. Because the verifier learns the programs to be zero knowledge, they have to learn nothing other than the stable. Here, they don't really learn that the two graphs are different, but they learn this thing is different. Alright, so it's clear. Yeah. All right. Who's ready to figure this out? So I realized that perhaps I made this like just a smidgen harder than I usually do, because normally I write down how we do the points a little differently. So let me just tell you about another way to write down what we do to the points. So it's basically the same thing, but instead of sending both things, you just send over like a permutation of one of the coins. So right, I don't know if you saw when I was checking the coins up here, but I only ever looked at one of them. Right, I just had to see if the one in my right hand changed or not. Right, it doesn't really matter. Once I know whether this was the same or different, I don't really have to see the other one. So you could have just sent me, the permutation of the coin. I'm writing it this way because when you have computers sending stuff back and forth, you don't want to send redundant information, and really, yeah, you just have to give me the coin in the left hand, like send that over. And then I have to say whether it swapped or didn't, by which I mean that you send over like 1 or 2, a bit. And then you check whether that bit is the one that you sent. Right, essentially you're sending me a permutation of the coin and I'm telling you which coin it is. Right, it's either going to be the first coin or the second coin. Okay, that being said, we can just, change our C here to a G. So we've got the verifier can just take a random permutation of G1. So they take this matrix, they just apply a random permutation to it. They send it over to the prover, and they ask the prover, which graph is it? The first one or the second one? And if they were the same, then the prover would only have a 50-50 chance at guessing, because it could be either one. It's a random permutation. So just like with the coins, you hand one over. If they were the same, it's the same coin. I don't know which one you started with, but I have to tell you kind of which coin you started with here. In this case, graph. So the thing about most zero-knowledge proofs is they're not actually going to take advantage of the structure of the things you're talking about. It's going to be more like a logical, I'm using the fact that these are not the same or are the same kind of situation, or that G1 is the same as the permutation of G1. If you try and go into the details, you're like, I'm going to reveal some small part of my permutation, and I'm going to, trace a path through the graph and all these kinds of things, you're bound to run into the problem of it not being zero knowledge. Because the verifier is going to end up learning something. And we'll talk about how to model exactly this fact and what I mean by learn something in a moment. But do people understand what I've done by changing this C to a G? Does anyone have any questions? Where essentially, we've got these two graphs, the verifier sends over, in practice they could send over this one or this one. Maybe, actually, they're probably supposed to. So they pick one of the graphs, they send it over, but they mess it up first. They randomly permute it, and they send it over. And then I have to tell them which one they sent over to me, the first one or the second one. And if I'm honest, and they were different, I'll be able to tell them apart, because I have unbounded computational time, I can just brute force it, whatever. And if I was being dishonest, then this could be, this is the same as both of these, because they're the same as each other. And so I'll have at best a 50% chance of success. And I claim you didn't learn anything, because I'm just telling you something that you literally already know. Right? You picked B, I'm telling you what B is. Just like when we were swapping coins behind backs over here, I just told you what you did. You didn't learn anything because you already knew that. All right. Any questions so far? This is a zero-knowledge proof. We're going to try another one now. I'll give you a bit longer for this one. So showing things aren't the same, easy enough. Hopefully you can imagine that this kind of generalizes anytime you want to show two things aren't the same. You can essentially just do this. But what if you want to show two things are the same? So in particular, P over here, they have some graph G1, and they know a specific permutation of G1, G2. So the prover can know how G1 and G2 are related, right? I've got some way of relabeling G1 to get G2. So this is what it means for them to be the same. I'll write the same by P. All right. So now I want to have a conversation again between the prover and the verifier. And again, it won't use any specifics. You don't have to have graph theory for this talk. Beyond, but this is a graph and you can write it down if you want. But I have two graphs. One is a permutation of the other, the prover knows it, and they want to convince the verifier that G1 and G2 have a permutation between them, that they are the same, in zero knowledge. Any questions about the next assignment? Other than, what on earth am I supposed to do? Which, I'll give you a couple of minutes, maybe I'll drop a hint or two. All right. Have a shot.
Nothing at all.
So just like last time, both the prover and the verifier know G1 and they know G2, but only the prover knows the permutation between them. So you can think of the pair G1 and G2 as the public key, and the permutation between them as the private key. It's probably a matrix, but it's a permutation matrix. Yeah.
Yeah, I feel like I was
exactly, yeah, so, yeah, exactly, make permutations, sometimes if you're in a place where everything is going to get somewhere where you're going to
Last time, it was just like this one. One of those graphs. This is all up. Without changing what I I mean, like how I play like ABC this right. If I switch that's what I
In this example, we're proving that we know communications.
I dropped a small hint on the board.
So in this example, we're supposed to prove that we know not that we know, we know the formula.
But really here, we just have to prove that. And being able to prove that is essentially going to turn out to be the same Yeah. So the interesting thing to solve this problem is all we're doing is showing these two things are the The issue is that that is agree that the verifier doesn't know that it's trying to well, yeah, verifier just has right. Yeah, so that permutation is like the private. It's two graphs of the verifier.
Random data, run it through permutations, and then exchange the result.
I'm not sure what I'm trying to say. You're right. I'm going to have this.
So you come up with like
what is that? I'm still not quite sure how to do this.
I'm lost.
Yeah, it's because you haven't been here.
I see a matrix of the bottom left.
But it's just a representation of that graph. It's a 1 if they're connected and a 0 if they're not.
What does it mean when it's mustache equal sign?
That means that there's a way to relabel one of them to get the other one.
What does it mean to relabel something?
Well, I wrote ABC on that graph to get this matrix, and if I wrote BAC, I would get a different matrix.
So
but those two matrices are the same.
But if I relabeled it, I would get G2 or GZ?
G2.
G2. So if I relabeled ABC to something else,
yeah,
I could get G2.
Yeah.
And
your relabeling is P.
But isn't that obvious? This is just
that's why you have to take a really, really big graph, which gets a really, really big matrix, and if I give you two of these things, and I'm like, I claim these are the same, you're not going to believe me, and I have to convince you.
And then how do you convince me?
That's what they're trying to figure out.
Who's trying to figure out?
All of them.
Well, how are they going to figure out? That sounds like a really hard problem.
Yeah, we've done some examples.
I like that you're good at answering my questions, by the way.
Whereas here it's clear. All right. One last hint. Just like last time, and basically most zero-knowledge proofs, the end of it is going to be a challenge and a response to that challenge. Yes? So the new thing I've mentioned here is that before the challenge is sent over, last time it's just a challenge and a response to the challenge. This time there's going to be a little bit of setup. The prover is going to send some third graph, you can decide what it is, over, and then the verifier is going to send over a challenge. And then if the prover's honest, they'll be able to satisfy that challenge, and if they're dishonest, they'll sometimes fail to satisfy that challenge. So this is going to be a challenge, and this is going to be a response. So I'll give you a couple more minutes.
I have a question. I thought that I found an approach we didn't need a setup, and I want to verify this correct.
Okay, let's go on. Go ahead.
So what you could do is the challenge you could give is basically you could either introduce an egg or not. So what you provided, yeah. So you could introduce an egg. Yeah, basically you could flip a bit in G1 or G2. Okay. That's something you could make. And what you provide is basically the permutation matrix as a verifier. And you send permutation matrix G1, permutation matrix G2. And then the prover can easily check by also applying his permutation matrix as well to see what's the same. And then he can say nothing happened, it's good. Or you could flip a bit and provide two matrices which,
The problem is if these are different, the prover will still be able to satisfy that challenge. So remember the two parts of convincing is dishonest prover might fail, but also, I think it's bad because the dishonest prover could still succeed in this challenge.
Got it, yeah, okay,
yeah.
Makes sense.
Yes, but good idea.
Okay, cool.
Okay, does anyone have a guess at what they want G3 to be? What could it possibly be?
CAB.
You mean a permutation of my graph, yes?
Yes.
Okay. Cool. Yeah, I mean, I'm not going to send over some random stuff. That doesn't really do anything. It's got to be related to my setup, right? So G3, we're just going to have, I realized that I didn't set up my board correctly to have space, but the prover is going to start by picking another random permutation. What are people's next favorite letters in English for permutations after P? E?
Very easy.
Y'all are crazy. Oh
ZBD.
Oh, sorry, did you say Z or E? E, okay. It's funny because yesterday when I was writing a bunch of letters on the board, everyone was like, never write E. And I was like, yeah, I mean, I guess. But okay, fine. Well, E is our permutation. And G3 is just going to be some other permutation of one of our graphs. Say the first one. You can do the second one. It doesn't matter. Because they're the same. Right? Okay, so we're sending over another permutation. This is just a shuffling of my set, kind of like I was doing with the sudoku. All right. And what could the verifier then ask the prover to do? We've got G1, we've got G2, we've got G3. The claim is that they're all the same. How might you challenge that? G2. And you know, they go both ways. routers. They're routers.
Would the verifier provide E to the prover so that they have the permutation?
So the verifier does not know what E is. E, again, is just a random permutation. Only the prover
You're
knows.
asking them to prove that they have this permutation.
Say this again?
You're asking, so the verifier is asking the prover that they have E. Right?
Yeah, we're trying to convince ourselves that such a P exists.
So when you provide them with E and say, use this to produce E3,
Who could do that? The prover could send E?
verifier sends E to the prover.
So E is something that the...
Tell him off track.
That's all right. No, you're very close though. So yes. I think... So, yeah.
The verifier could ask, can you produce G2? Can you use it from the first step? The verifier can say either G1 or G2.
Okay.
If the prover can prove that G8 is equivalent to G2, we know it's good, and we can.
Cool. So the verifier picks one of G1 or G2. They pick a bit, and they send that over as a challenge. They're like, show me that G3 is the same as G1 if they send over 1, or show me that G3 is the same as G2 if they send over 2. Right? So we're not allowed to literally reveal that G1 and G2 are the same by revealing P, because that would not be zero knowledge. It would be convincing, of course, but it wouldn't be zero knowledge. So we just introduce this third thing, and then the verifier challenges with a random bit, saying, show me that it's G1 or that it's G2. And if B is 1, then they respond with E, and they just send E over. And if B was 2, then they respond with, let's see, E sends G1 here, so I do E inverse composed with P. So I have these two permutations. I could do one and then the other and represent that as a permutation. This is kind of like the addition of permutations, so to speak. So right, if I put G3 into this, then it'll spit out G2. So we had this nice interactive proof that was convincing of just revealing P. That's not zero knowledge. To get a zero knowledge version, we introduce a random third thing that's the same as both of these. And then we've shown that G1 and G2 are the same by showing they're the same as something else, without revealing anything about the relationship between them.
If you can prove or convince that G1 and G3 are equivalent, and then you're saying that zero knowledge proof is proving that G3 somehow can drive G2, or what was that?
So to be clear, this is, again, like the previous example, something that we're then going to repeat with a new G3 each time. Right? We just generate a random permutation each time that we do this, and each time the verifier can either ask us, show us it's the same as G1, or show us that this new random thing is the same as G2. And if G1 and G2 were different, it can only be the same as one of them. So half the time we're going to fail. Right? And so if I keep on succeeding, there's only like a 1 over 2 to the n chance, if we've done this n times, that I've just gotten lucky each time. Which we can make that as small as we want.
Okay, I get it, because it's interactive.
Yes.
So if it was, okay, but this is, the whole talk is on interactive zero knowledge?
Yeah, so wouldn't it be great if we could, someone over here told me that the verifier, all they're doing is sending over random bits. When we were doing coin flips, when we were showing graphs aren't the same, when we're showing graphs are the same, they're just sending over random bits. Wouldn't it be nice if we could just get rid of them with something that spits out random bits, so that it wouldn't have to be this interactive back and forth? That would be great. We'll get back to that. That would really be great. Yeah. There certainly are non-interactive zero knowledge proofs, but so far we're just looking at interactive ones. Yes. Good. All right. So yeah, we produce these third things, and we only have a 50% chance of being able to show that they're the same if G1 and G2 weren't the same, and we have a 100% chance of being able to do it if they are the same. We just give them this or this. Now, a question I usually receive Doesn't that give away information? What do people think? Because right, I'm not allowed to tell you anything about P. Why am I allowed to compose P with E and then give you that? Right? Okay, so I said this intentionally. Composition between, like if I do one permutation and then another, and I write it down as one permutation, that's like addition for permutations, and adding a random number to something results in a random number, right? If I have my secret key, X, and I add a random number R to it, and I give you X plus R, you've learned nothing about X. It's just a random number. It has an equal chance of being any number if I add a random number to it.
If the verifier wasn't picking random numbers, you say we got this on this verifier, shouldn't that reveal to
Yeah. So if they aren't picking random numbers, what are they doing? Well, anytime they pick one, they just get a random permutation. So they learn nothing there. And if they only pick two, they just get P plus a random permutation, which, as I mentioned, is just the same as a random permutation.
And I'm here to help.
So it's the same as if they sampled from random permutations.
Got the Wi-Fi there, and we'll have your PC.
Sorry.
No worries. All right. So I want to try and address these concerns. Let's try and be a bit more precise about what it means to be zero knowledge. So how can I determine whether or not something is zero knowledge? Well, the key word that I tried to throw in there was that the verifier learns nothing useful. So how do you determine what's useful information and what, like I claim these things are useless information? So the key is that we want a verifier to not be able to do anything with these conversations that they couldn't do by themselves. So we say the transcript of this zero knowledge proof is just the triple of a graph, a bit, and the response, which is some other permutation that we'll call a letter. Okay. Next time I'm using Greek letters, I've decided. Okay.
What's wrong with that letter?
It's gonna mess me up.
Well, then choose a different letter.
No, I can deal with it.
All right,
I'm a professional.
All right.
But it might mess you up when you go and read the papers later, because K's are going to be used for different things. But this is better for now. Okay, so we have this, and we have a bunch of these. So if the verifier learns something, what I mean by that is that from a list of these transcripts that they have with the prover, they can then use that as an input to some program to go do something. And so they learned nothing if they can generate something that looks just like a transcript with a real prover on their own. Because then anything they could do with it, they could have done on their own without a real prover. So we call this simulation. So we're saying that it's zero knowledge if the verifier could simulate a conversation with the prover. So what does that look like here? Well, the key thing is that they don't have to go in order, right? If they're generating one of these transcripts in a simulated sense, what do these look like when they're talking to a real prover? Well, you get something that's sampled from the set of the set of permutations of G1, right? G3 is just a random permutation of G1, meaning that it has the same chance of being any permutation of G1. B, half the time it's 1, half the time it's 2. And K is such that K of G3 equals GB. But okay. So K is just the thing that takes G3 to the specified graph. Okay, how might a verifier make a fake, pretend they talked to a real prover? Well, they can start by picking K, and write K is just at random. So they pick a random permutation, they pick a random bit, 1 or 2. They know what they're going to challenge with. And then they pick a K, which is just a random permutation of that graph that they picked. And then they just write down the G3 that makes it work with that K and that B. Right? So they can generate random bits, they can generate random permutations, and then they can generate the G3, which since K is a random permutation, this is just a random permutation. And so whether I sample from actually talking to a real prover, or whether I sample from just making stuff up, I get the same values both times. I get the same distribution on transcripts for the chance that this is the conversation I had is the same as the chance that I had it from generating over here. So in some sense, the prover doesn't provide anything that you couldn't have done on your own. That's why sending over random data is okay, because a verifier can generate random data. So this is a bit technical, and it's okay if it doesn't click right now, but hopefully some seeds are planted and we can try another kind of zero-knowledge proof. Time? Yeah. Do I want to, or do I want to talk about Schnorr? I want to. Okay. So, now I want to talk about Schnorr. Y'all care about Schnorr, right? Let's make this about Bitcoin. Okay. So far we have zero-knowledge proofs, which are conversations between provers and verifiers that are convincing, meaning if dishonest provers fail, honest provers succeed, and zero knowledge, meaning the verifier doesn't learn anything useful, or in other words, a verifier could write down something that looked like a conversation with the prover, and if they generated a bunch of these things, and then they had a bunch of actual conversations with provers, no one would be able to tell the difference between those two things. And so anything they could do by talking to provers, they could actually do on their own. Okay? So, going back to Tidwell and others' questions about, like, can we get rid of this verifier? Yeah, let's do it. So, they're just generating random numbers. What is something that generates random-looking numbers?
Blockchain hashes.
Hashes. Yes. Let's replace the verifier with a hash. So I'm just going to have a hash function. And what is it that I'm going to hash?
The block.
I'm going to hash the context, right? So in this case, it'll be G3, it'll be G1 and G2, it'll be anything that is like around in the context. So you have all the stuff in the context, you just throw it all into a hash, and then the output of the hash, that's going to be your challenge. So for example, just take the first bit of this hash and use it as the challenge. Or conveniently, let's just use each bit as an individual challenge because we want to repeat this thing until we get a good probability, right? So we're going to take each bit of this hash and have that be one run through of a challenge, and then we're going to generate responses to those challenges. I guess, yeah, in this case it'll just be one bit, but in the future you can be a bit more efficient. But okay, point is, we can replace the verifier with a hash function. And now what does it look like? I am going to write down a G3 and a response, K. G3 and K, right? And then when I send this off to someone, say I send this to Tidwell, Tidwell knows G1 and G2, right? They're the verifier. Everyone knows G1 and G2. That's my public key. And then Tidwell is going to verify that if you take the hash of G3, G1, and G2, and you use the first bit as a challenge, that this is a valid response. So all of a sudden, I can just send this around, and it acts just like it would if I talked to a real verifier, but now it's non-interactive.
But if you keep the G3, you could decide to withhold all the G3s that don't work.
Sorry?
Yeah, I don't get it. It's like, so suppose you're the prover, and then like the randomness comes from the hash of the G3 you provide. What you could do is you could take the G3, you could take the hash and see, oh, this doesn't work, I generate another one. oh, this one works, I publish that one. So
when you say works, what do you mean?
yeah, suppose.
Like it'll always be
Suppose
one?
you're cheating me, and then you have a 50% chance of failing if in the challenge. But if you have the cheat tree, you can compute the hash. You can see, oh, if I publish this one, I get caught. And then you don't have, and then you just decide to take another cheat tree. So you basically, I don't see what you prove at this point.
Yes. So this is kind of weak because we're just using one bit of this hash. So we would have to do something a bit stronger. So let's get rid of all of our graph stuff and say what we're really talking about. So I'm going to replace our public key and private key. We now just have a private key x, which is a number, and a public key capital X, which is its elliptic curve point. So that's, if this is the private key, just a number, then this is its Bitcoin public key. Yeah? Okay. And now I generate a random k, oh god, which is just a number, this time. I'm going to slowly erase everything we've been talking about and replace it with Bitcoin stuff.
I get a cursive K.
Then we send over R, where R is just the public key of K. Yes, so just like earlier, I generate a random number and I take its public key. And now over here, I'm going to take the hash of R, capital X, right there, and that'll give me a number, which people call E. I'm gonna erase all these other markers. And they send that over as their challenge. They pick a random number, of course, a random E, but when we replace them, it'll just be this hash. So E is random. Random number. And then the response is going to be K plus X times E, which is usually called S. And then the verifier checks that S times G equals R plus E times capital X. Okay. So just like before, we start by sending over some random stuff. We get a challenge, which is just a random number. And then we respond by building something where we hide using our randomness. We're adding a random number to it, so it's going to be randomly uniform. We're not going to reveal any information. But it uses our private key and the challenge. So it's quite simple, though I won't do it here, to prove that you couldn't generate this number without knowing the private key and applying it to the challenge in this way. And then you send this over, and then the verifier just checks that the public version of the math works out. By which I mean you just take these, this is a number, right? This over here is a number they don't know, this is a number they do know. But they know what elliptic curve points go with both of these, because they know R and they know X. So those are public. And so replacing them, what this looks like is you have to send over, if you're generating a proof that you know the private key to this public key, then you send over a random point R that you know the secret behind, and you send over S. And then when someone comes across this R and S and they know your public key X, then they know what the challenge was because they look at this hash. Now you'll notice we're using all the bits of this hash. So trying to fake this hash by picking different R's isn't going to work because you're going to have to get like, yeah, there's a proof for it and it's definitely out of scope for what we're talking about.
But this R and S, if you come across it, you verify it by checking this exact equation, where E is the hash of the context. Now, usually, people like to add something to the context. If you're trying to prove who you are, you usually do it by, like, having something in a context that gets added, namely, like, a message. So you can add a message into this context. And now this is a digital signature. It's a proof that I know this. And the reason you add the message is because you don't want replay attacks, right? Normally the message will be something like, Nadav owns this key, which, like, why would someone else sign it, right? So you add this message of what it is I'm trying to prove or what it is I'm trying to sign. Like, Nadav approves of this Bitcoin transaction. And we add that into the context. And then we have this zero-knowledge proof of showing that I know the private key to a public key, just like I showed that I know the private key of a permutation to the public key of two different things. Essentially, if you take any computationally hard problem, you can kind of turn it into an identity protocol in this kind of way, where you generate some random stuff, send it over, take a random challenge back, and then use your secret key and the challenge to generate a response that can be verified. And anytime you do that, you can replace the verifier with the hash function. And then you just get a digital signature. So ID protocols become digital signatures by just replacing the verifier with a hash function. Whew. Any questions before I say some fun things about what kinds of things have zero-knowledge proofs and what kinds of things don't? I feel like I've been talking for too long. Clarifying questions, repeats, anything? Yeah?
There's still you said you made it non-interactive by replacing the verifier with the hash function. You still have to compute your volume there in the end. So there still isn't a verifier.
Yes, but you'll notice the verifier had to be part interactively of the construction earlier, and now there's just verifying the output, which is exactly what we want. So when we say non-interactive, we mean that this is a proof, but of course, you know, you have to check the proof. So the proof is constructed non-interactively. The verification of the proof is still required. Yes, good point. Any other questions? Okay, so lastly, you might wonder what kinds of things can you prove in zero knowledge, right? Like, we talked about showing graphs are different. We talked about showing graphs are the same. We talked about showing that you know the private key to a public key. I showed you sudoku, which you'll notice also had this shape, where I generated a random permutation and then gave you a bunch of, you can think of it as encrypted cards, and encrypted the permutation, and then you challenged me by either saying, give me the rows, give me the columns, give me the squares, or give me the setup. And then I respond with, like, the keys to decrypt those things. I flipped over some things. And so this shape is kind of very prominent, and it's called a sigma protocol. Any guesses why? So a Greek sigma looks like this. It's a capital letter. And so that's why we call it a sigma protocol. It's really stupid. Is it drawn backward? No, I can't draw it. I always get confused whether it's a... Some people write P and V in the other order, and I don't know which one makes it a sigma, but one of them is a sigma, right? Okay, so this is called a sigma protocol, but to confuse you, everyone uses lowercase sigma.
That's not because of the shape of the exchange.
Is it, sorry?
It's not because of the shape of the exchange.
Oh, is it not?
It was somehow tactile nature.
I see, okay. Well, now you know the myth, and you're just as confused as everyone else. Awesome, we're all on the same page. I believe it's not this. I mean, it's funny that it looks like it, but why is it a sigma protocol? Who knows? Not me, probably someone. Okay, but any problem, if you know your complexity theory, any problem in NP has a sigma protocol. And we actually proved it. So if you, there's this class of problems called NP-complete, which are like the hardest problems in NP. Any problem in here, any problem that you can check efficiently, right? Checking a solution to a Sudoku problem is really efficient. You just check all the rules. Checking, I guess that's the NP-complete thing we've looked at, because I skipped the other one. But anything in NP, anything that can be checked quickly, can be reduced to a problem like Sudoku. Of course, I don't mean literal 2x2 or, 4x4 or 9x9 Sudoku. It might have to be like an even bigger thing. But the proof that I gave for how to do a Sigma protocol for showing that you know a solution to Sudoku works for any sized grid, right? Just rows, columns, boxes, and set. You just check those things. So we have a Sigma protocol for something in NP-complete. So anytime you have a problem in NP, for example, showing the private key to public key, checking, if I just gave you the private key, checking that I was right would be efficient. So that means that it's an NP. NP does not mean not polynomial. It means non-deterministic polynomial, which is the same as polynomial time checkable. Yeah, very confusing naming on their part, but anything that you can check efficiently, you can literally write down a protocol like this, and a really dumb way to do it is you reduce that problem to Sudoku, and then you do the Sudoku thing on the same problem. All right, but there's an even bigger class of problems called P-space. No small children around, clearly. P-space is all the things that you can do in polynomial space. So think about all those brute force things you can do without using very much memory. All of those problems. This is like a huge set. It turns out that it's exactly the same as the problems that have interactive proofs. So that's the zero-knowledge proofs without the zero-knowledge part, just convincing back and forth. And then the big result that I want you to take away is that all things provable are provable in zero-knowledge. This is a theorem from 1990. And it basically says that if I have a way to convince you of something, I can do it without revealing any of my secrets. So when I say a way to convince you, I mean if I could convince you of something by giving you all my private keys, all the private keys I own, and then I'm like, see, I did what I told you I did, and you could check it, then there is a way to do it in zero knowledge, without revealing any information at all about any of my private keys. So this is really big for cryptography and for things in Bitcoin. Zero knowledge proofs are useful when you're like, man, I wish I could convince you I followed some rules or that this thing was generated from these other things. And if I could just show you my private keys, then it would be possible to do that. Well, then there is a possible way to do that. And there is a zero knowledge proof to convince you that I followed the rules.
Is it proven that that zero knowledge way is practical, or could it be the case that it's so hard to compute that you actually might not even do it for this calculation?
So it depends on your notion of practical. As you might know, academics, when they say polytime, they're like, oh yeah, that's great stuff. You know, that's a polynomial, that's tractable. You could make real money off of that. But like, you know, here's a polynomial. Like, you know, I could put a big number in front of it.
Let's put it another way. Is there a bound on the complexity of actually generating the zero knowledge proof?
Yes, yes. So we have zero knowledge proofs that are good, especially if you're in NP. We have these Sigma protocols, where everyone's polytime and everything's fun. Yes, so we even have polytime bound. I don't know if there's something better, maybe there is. But, yeah, in practice, it is open research. And this is like what all those, you know, shitcoiners fund, is all this research about zero knowledge proofs. There's like a lot of things that we know theoretically are possible, right? There are theorems that prove it. We know inefficient ways to do it, but we don't know efficient ways. And so a lot of people do a lot of work on trying to find efficient solutions that are actually practical. Other questions? Cool. Well, I'm happy you all have suffered through enough. I see that we've all taken some hits today, and I'll grace you with an extra 15 minutes before your next workshop. But feel free to come and ask me any questions after, and yeah, if you really, I guess, are a masochist, I'm giving the same workshop again. I might do one or two different examples or something, but it'll be basically the same thing Saturday morning. So tell your friends to come to it or not to, if that's how you feel.
Bring the family.
Yeah, bring the family. All right, thank you.